Welcome to the demo for the SigFlow tool. This tool was made over the span of 5 years to make circuit analysis more automated, optimized, and intuitive. To boot up the tool, we need to give a schematic, netlist, and an operating point log file. They can be generated using LT-Spice, and the tool will be booted up once these files are submitted. The main feature of our tool is generating the signal flow graph from the provided schematic. We can pan, zoom in and out, and move around the nodes. The values on the signal flow graph are presented in numeric form by default. The tool can display its symbolic form by clicking this checkbox. After doing so, we can customize and manipulate the signal flow graph to yield a simpler graph. With the simplification operation, we can apply the signal flow graph equivalences by selecting the two nodes to simplify. We can also remove dead or insignificant branches, edit the symbolic value of the branches, and undo all these operations. We can also visualize the most significant path of the graph. You can modify the circuit parameters, such as the capacitance, resistance, and the frequency range as well. This is especially useful to observe the changes in gain and Bode plot, which will be described next. Given the input and output nodes, the transfer function and loop gain functions can be generated. We can toggle the checkbox to view the numeric form where we can derive the gain. Their Bode plots can also be generated. The red line indicates the gain plot and the blue line indicates the phase plot. As Bode plot data are saved, we can overlay a previous plot to compare and contrast the results. Now we will discuss features that we have implemented. We worked on an overlay feature to help users easily correlate the signal flow graph to the schematic with an automated node matching feature, a branch removal feature that automates the signal flow graph simplification operations, and a stability analysis feature to observe how the stability of a feedback circuit changes as a device's value change.
So let's start by discussing why the overlay feature would be a good addition. Originally, the motivation for making the application was to take a circuit schematic and generate a signal flow graph from it. Now, having that signal flow graph is great, as it converts complex circuits into graph-based representation for more intuitive understanding. However, understanding the SFG and the relations within the SFG could still be very challenging, especially as the complexity increases with increasing number of components. Like in mapping applications, the several layers that are put together might not make so much sense individually, but collectively, they are more helpful and they make applications like Google Maps that we so often use. Now, similarly, overlaying the SFG on top of the schematic improves traceability. So specific paths and nodes can be more easily identified, and this makes it easier for the user to see the relationship between the physical components in the circuit and the representation in the SFG. Not only is it helpful for the user, it is also helpful for us, the developers of the application, as it allows for easier verification and hence easier debugging because in case of an error, we can pinpoint the error to a specific section in the graph. The team has managed to stack the circuit and SFG on top of each other and is now working on node-to-node matching. And in the meantime, the SFG continues to be interactive to allow users to manually move around the SFG components.
The purpose of branch removal is to get rid of unnecessary branches to make the circuit easier to read and understand. So first we'll get rid of the trivial branches, which is done like this. And then to get rid of the weaker paths, it's done like this. In this example, we are trying to find the paths between the source VB in and the destination VB out.
Now onto the stability analysis feature. To provide some quick background on the stability of feedback circuits, as phase shifts accumulate in a feedback loop, the circuit can become unstable, leading to oscillations. To address this, capacitors are often used. Stability is assessed using the phase margin. A larger phase margin indicates a more stable circuit, while a smaller phase margin signals the risk of instability. However, this comes at the cost of reducing the circuit's bandwidth, which is the range of frequencies over which the circuit operates effectively. Our stability analysis feature enables users to evaluate how different values of a device affect the phase margin. We need to first give it the input and output nodes. We can then select a device such as the capacitor or resistor. In our demo, we will sweep C1 from 10 to 100 picofarads with a step size of 10 picofarads. These inputs allow us to analyze how changes in the device's value influence the circuit's stability and bandwidth. Based on this, we generate two plots, a phase margin plot which reflects the circuit's stability, and a bandwidth plot which shows the range of frequencies the circuit can effectively handle. As you can see, the results are consistent with the transient output if a C1 capacitor was swept with the same range and step size on SPICE, because the plot appears to look less oscillated as the capacitance value increases. We're looking to hear about your feedback on the tool, like the intuitiveness and helpfulness of these features, and if there are any more desired features, whether it be related to the user interface, analysis aid features, or automation features. Thank you for your interest in the SigFlow tool, and we're looking forward to hearing your feedback.